Hey everyone, so we will be talking about Module 4. This module has 4 sections: balancing equations, limiting reagents, percent composition, and empirical formulas. So let's go ahead and begin with the first section. Okay, so for balancing equations, what we are trying to achieve is to conserve the mass. So basically, the number of atoms on one side of the chemical equation has to be the same as the number of atoms on the other side of the chemical equation. So both the reactant side and the product side should have the same number of atoms, although they might be arranged differently. So in order to have um, all of these atoms be equal, we're going to have to rely heavily on coefficients. So we're going to work on some examples right now, and I'll explain a little bit more. Okay, so we're going to start with a simple chemical equation and then build our way up. We have hydrogen gas here, we have oxygen gas, and it all yields water, H2O, in liquid form. So real quick, just to refresh your memories, remember whatever is on the left side of the arrow is called your reactant side. So this is where you find your reactants. And your products are found on the right side of the arrow. So where the arrow is pointing, and then the arrow itself is called the yield sign. Okay, so remember, you're going to have some subscripts here. Right here, even though you don't see one, there is a 1. Okay, but you don't have to write a 1 there. So I'm just going to erase that. Just keep in mind that you do have a 1 there. And right here, in between where we have these spaces, is where we are going to write our coefficients. They're the big numbers that we're going to use to multiply the subscripts with. Okay, so what we are going to do first is write down all the atoms that we have on the reactant side and on the product side, which should be the same, of course. So on the reactant side, we see that we have 2 hydrogens. And then on the product side, we see that we have 2 hydrogens. So far, we do not need to change the coefficients, right? So now we look at oxygen. We see that it has 2 here on the reactant side, but on the product side, we only have 1. So what we're going to have to do is multiply this by a coefficient of 2, so we can end up with 2 oxygens. The only problem is that when we place the 2 here, not only does it change this oxygen to 2, but we will also have to multiply the hydrogens. So now we're going to multiply 2 times 2, and it's going to give us 4. So we end up with 4 hydrogens, and if you look over here, we only have 2. So what we can do is multiply this number by 2, and we can end up with 4 hydrogens now. So remember, this number that we're multiplying with is our coefficient, the big number that goes in front. So a 2. So now if you check, 2 times 2 is 4. 2 times 2 is 4. And then right here, we left it blank, but there is an imaginary 1. You don't have to write it, but if that helps you, you can write it. So then we have 2 oxygens here. 2 times 1, 2 oxygens. So now we have a balanced equation. So let's go ahead and try another example, a little bit more complex. Okay, so for our next example, we're going to look at the following chemical reaction. Barium fluoride plus potassium phosphate yields barium phosphate plus potassium fluoride. Okay, so again, we're going to do the same thing. We are going to list all the atoms that we have here. Then I'm just going to write them in the same order so we can compare them side by side. So if you notice for polyatomic ions, I'm just leaving this whole thing together. I'm not going to separate it by phosphates and oxygens because that's going to take more work and it might be more confusing. So barium, we have 1 here, and then we have 3 on the product side. And if you want, you can maybe pause the video so you can write this information down on your own and try to solve it and then come back to look at the solution. I'm just going to write this real quick. Okay, so we know that all these numbers have to be equal, so barium can be multiplied by 3 in order to have the same number as the product side, right? So this is going to be the coefficient that we're going to write here in the space. Remember that you distribute to both elements or whatever elements are present. So this is also going to change the amount of fluorides that we have. So 2 times 3 is going to be equal to 6. So now we're going to have 6. But if you go to the product side, we only have 1. So we can multiply this by 6, right? So we can have 6 fluorides. Remember, this is going to be the coefficient that we're going to put here. So 6 times 1 is 6, but it's also going to distribute to the potassium. And remember, we have an imaginary 1 here. So 6 times 1 is going to be equal to 6. So now we're going to have to go and look at the potassium on the reactant side. And we see that we still have 3. So what number can you multiply 3 by in order to get 6? And this one is really easy. You can multiply it by 2. This is going to be the coefficient. So you're going to look for potassium, and here it is. And we're going to put the 2 here. So 2 times 3 is 6. And this also distributes to the phosphate. So now we have 2. And right here, we already have 2. Okay. So right here, you can write the 1. Or you could just leave it like that. Whenever you leave an empty space, it's implied that you already have a 1. So your coefficients for this chemical equation are 3, 2, 1, and 6. Okay, so for our next example, we have the following chemical equation. I already listed all the elements that we have present on both the reactant and the product side, which should be the same, of course. And I'm just going to write down how many of each I have. So we have 4 carbons, 8 hydrogens, and then we have 2 oxygens here, and then on the next portion we have 2. So I'm going to write them like that. So keep in mind that we have those 2 separate oxygens. Product side, carbon we have 1, hydrogen we have 2, and again we have the same thing, so I'm going to list them like this, 1, 2. So we have 1 oxygen there, 2. Okay, so what I always like to begin with is carbons. So I can multiply this carbon by 4 to get the same number. So this is going to be our coefficient, 4. Remember, this distributes, so 4 times 2 is going to be 8. Okay. So let's leave the oxygens for last. Now we're going to look at the hydrogens. We have 8 hydrogens here, but we only have 2 here. So we can try to multiply this by 4 to get 8. Then insert this coefficient here. So 4 times 2 is 8, as we already said. And then we're going to multiply this one by 4 as well, because it's attached to the hydrogens. Okay. So now that I have my coefficients for both of these oxygens, I'm going to add this. And it comes out to 12 oxygens in total in the product side. Okay. So we already know that these are good, right? We don't need to add anything onto it. So this is going to stay like that, added to. But we need to have a total of 12 oxygens. So that means that we need 10 more because we already have 2. So what can we multiply the 2 by in order to get a 10? And it'll be a 5, okay? So then your coefficients are 1, 5, 4, 4. So we're going to cover one more example. The following example might be a little bit harder because it is going to include fractions. So for our last problem, For balancing equations, I have the following equation. I've already listed the elements that are present and how many of each I have. Remember, on this side, we have two compounds that have oxygen. So that's why I listed these separately. So in one of them, we have two oxygens, and the other one, in water, we have one oxygen. So I'm going to start with carbons because they're easier for me. So we have two carbons on the reactant side, but the product side only has one. So a number that they have in common that we can multiply it by is 2. So the coefficient of 2 will give us 2 carbons. So we're going to put it here. Okay, so remember this distributes. So we're going to multiply one of the oxygens by 2, and it will give us 4. So now we have a total of 5 oxygens, but we're not going to balance the oxygens yet. We're going to move on with the hydrogens. We know that we have 6 on the reactant side. So this 2, we want to turn it into a 6, so we're going to multiply it by 3. So this coefficient, is going to give us 6 hydrogens. So we're also going to multiply this oxygen by the 3. Okay, so now that we know the coefficients for all the other elements, we're going to add these oxygens, and it gives us a total of 7 oxygens on the product side. There are no whole numbers that we can multiply this 2 with in order for it to give us a 7. Okay? So this is where fractions come in. Remember, I was telling you that they might be a little bit more confusing. So when you already know that everything else is balanced correctly, and then you get an odd number for your oxygens, simply what you're going to do is that you're going to use this number and turn it into a fraction. So it'll be your numerator, okay? So the 7 is going to go on top, and then you're going to use this subscript as a denominator. Okay? So now you're going to have 7 over 2, and this is a 0. So you can double check if this is correct or not, if this actually gives you 7 or not, by multiplying it. So multiply this coefficient by this number. So distribute. And when you multiply 7/2 times 2, it gives you 7. You can check it in your calculator or just do it in your mind. Okay? So our coefficients for this problem in specific are as follows. So again, remember, whenever you have an odd number for the oxygens, that means that you're going to have to use a fraction. So the odd number is going to go on top. In this case, in our problem, it was on top, and then this subscript was used as a denominator to create this fraction. To double check it again, you would just multiply this new coefficient times the subscript that you already have here given to you, and it should give you the same number as the opposite side. In this case, the same number as the oxygens in the product.